cases in accuracy. In most of the meteorology book, when you see an approximation, most of the times it's coming from Taylor series expansion. So this is what you have learned in the math course, Taylor series expansion. So if we want to express an equation, for example, sine x here, which is the black curve in here, we can expand this into infinite number of terms, and then the more terms you include in your approximation, the more your solution or your expression is close to this one. So for example, if you want to express this sine x, and then you take the first two terms, and your expression will be looking like this one, sine x equal to x. Okay, so in this way you are approximating the value around a value, approximating sine x around this value a in here. So you know that x is really small, it's a small number, and then you can approximate sine x around this x equal to a value, which is 0 in this case. Okay, so you can see that the more terms you include, for example, if n equals to 3, you include 3, this 1, 0, 1, 2, 3, and then 1, 2, and 3. If you include 4 terms in your approximation, your approximation will be looking like this. So this is a little bit more close to sine x than using the first 2 terms only. So you know how this works. So I'll do a revision with you anyway. So here is just copying the Taylor series expansion. So if we want to, so this f prime here is this one, and then 2 times here, it's this one, okay? And then you know the expression for this, we differentiate it n times, okay? And then we perform this on sine x around the value of a equals to 0, okay? And we know that fx is sine x, right? And then we differentiate it 1 time, and then it's cosine x, and differentiate it 1 more time, it will be minus sine x, and then 3 times it will be minus cosine x, okay, and 4th time it will go back to sine x again, okay. Okay, so how do we make use of this equation? We just plug in all the things that we know about Taylor series expansion. So we express this sine x, the first term. We know that a equals to 0, so we can substitute that. Cosine 0 x. Okay, so we know that this is 0. This also is 0. And then this and then we know that the even terms, it's obvious. It's obvious that terms with n equals to even number 0. Okay, so what we have left is that this equals to x here, and then this is x to the power 3. Sorry. Okay, so you know that for the first approximation, when you know that x is really small, this is how we arrive at sine x is approximated to x, which is the red line in the T1 approximation. Sorry, in here. Okay, this is the T1 approximation. Okay, so how do we make use of this Taylor series expansion? This is just what we just did. It's just a revision. Okay, so here, if we are in here, x equals to x in here, and then we want to know what will happen in the next time step. Oh, sorry, this is location. So if you're here and then you want to know the value of a certain variable at the next location, so this is the value of your variable at the next location. This is your current location, and this is the change of the location. Okay, we use this forward differencing to find this out. Okay, and then if you are here and then you want to find out what is happening on your back, this is backward differencing. Okay, and we can apply this. Okay, so forward differencing. We use Taylor series to find out the change from x to the next location, x plus delta x, and we want to apply it to equations like this. For example, this is the momentum equation. In the x direction. Okay, so let's say you have measurements of pressure. For example, this is your map, this is your grids in different locations, and then you have the value of P at different locations in here. P00 and then P01 like this. And then we want to use them to calculate the pressure gradient force. Okay, so we will blow this up and imagine Fx is P. X is the pressure, and we approximate F in the next location around your current location. Okay, so this is the Next, and your next location, the F in here. Okay, and then I'll copy the Taylor series expansion again. Okay, this is a mistake, sorry. Okay, so we are approximating this. So your new x is x plus delta x, and then your a is x. Okay, so we know that f prime is differentiating the expression f one time. Okay, and then we take this aside. Okay, so we divide the whole term by delta x. Okay, this is just copying this part. Okay, so these are the error of this approximation. Okay, so the approximation is just the first term in here on the right. This is how we arrive at this difference equation. Okay, and this error, we call this first order accurate. Because the largest term here, the largest term in your error is with delta x. Sorry, this is gone. And then, yeah, this is a mistake, sorry. So this is the largest term in your error with the delta x. Oh, sorry, this is not gone. Sorry about this. Here, this is gone. This is the largest term in your error. Okay, so the backward differencing is exactly the same, except that, so this is the forward differencing. We have just done this. This is the backward differencing. I can also do this with you. So backward differencing. Similarly, and then we rewrite this into a simpler form. Okay, and then we take this aside, and here the negative sign is coming from the minus delta x to the power 3. Okay, and we know that this backward differencing, which is we are working with the location on your back, x minus delta x. So what is the accuracy? What is the order of accuracy in here? It's the same as the forward differencing because this is the largest term. Okay. So next we talk about center differencing. So it's pretty easy. For the center differencing, we make use of this forward differencing and backward differencing, and then we mix them together. And we are still working on the first derivative, so they're all working on the same derivatives, but we use different methods in here. So this is center differencing. By center differencing, we're talking about using information from the front and then from the back. So we have provided more information to your calculation. Okay, so we combine the center for center differencing. We are combining the forward differencing and then backward. We have a minus here because we have a minus here. Okay, and okay, so this minus is coming from this. Okay, so this is 1, and then this is 2, and then 1 minus 2. So we have this, and then equals to 2, because we are doing the minus. We take these out. So you can see that only the odd terms are left. Okay, if we take this out, we know that this is the difference equation between the information in the front, which is x plus delta x here, and then on the back, x minus delta x in here. We have divided the whole equation by delta x, actually 2 delta x, so that's why this term we only have delta x squared left. Okay, so these are the error, and only n equals to odd number are left. This is what we call second order. Accurate or accuracy, because the first order error terms are cancelled. The largest term in here with delta x squared. So the order 1/2 is cancelled. Okay, so this should be 2 prime in here. Yeah, there's a mistake in here. Sorry about that. Okay, so we have increased accuracy. Accuracy increased, and then we know that this is widely used in atmospheric modeling. Okay, this is what we have just done here, the center differencing, and then we increase the accuracy. Okay, there is another way to further increase the accuracy. We have just done second order accurate calculation. if we want to increase the accuracy to fourth order, this is what we need to do. Okay. How do we start this? We need to replace delta x with 2 delta x in your center differencing, using 2 delta x instead. Delta x in the interval. So now the interval, if you're here, the interval is x minus 2 delta x in here, and then in x plus 2 delta x. So it's pretty easy, you just rewrite everything. Rewrite the delta x with 2 delta x, f plus 2 delta x minus, so this is still center differencing. But with the interval of 2 delta x. Okay, so to increase, this is still second order accurate. Okay, so to increase the accuracy, we want to get rid of the largest term in your error, delta x squared, right? Second order, so delta x squared. You want to get rid of this and then increase the accuracy. We use the center differencing. Center differences of the intervals delta x and 2 delta x. Okay, I'll open a new file in here. Okay, how do we combine that? We rewrite the derivative with this. So here, in here, this one, we put in the center difference of interval delta x, and then here we put in the center difference of interval 2 delta x. Okay, how do we do that? Okay, I'll rewrite this. Okay, and then we have to write the rest of the error terms. Okay, so the goal in here is to remove this. I'm sorry, there is a typo in here. This is 2. Sorry about that. Okay. We want to remove this because this is the largest term in your error. Largest terms in your error. Okay. So how do we do that? We can just rewrite this term first. Okay, minus. Actually, if we rewrite this, it would be like this. Okay, if we want to remove this, we want to make this, we want to set this 0, right? And in here, you know that a plus b should be 1. Now you have 2 equations, 2 unknown. We need to solve a plus b equals to 1, and then a plus 4b equals to 0. If we solve this, we know that a equals to 4 over 3, and then b equals to minus 1 over 3. So if we substitute these back to this equation, you know how to express your your first derivative with your center difference with delta x, and then center difference with 2 delta x. Okay, so this is how we arrive at this expression, the 4th order differencing for the first derivative. So first derivative is just differentiating this one time. So in here we are eliminating the largest error term with delta x squared, and then the largest error term would be with this one, delta x to the power 4. So this is why we call this 4th order. 4th order differencing, 4th order accurate. Okay, so next step would be doing second derivatives. So it's also pretty easy. Okay, how do we do that? Second derivatives. Okay, we have the Taylor series expansion on f at x plus delta x and on f x minus delta x. Okay, so we have the expression for both of them. And then the next one, x minus delta x. We have a negative here again because of the power of to the power of 3 in the delta x. Okay, so if we add them up, we will have a few terms left, these. So we adding them to eliminate f prime. What is f prime? The odd terms are gone. Odd terms are here. Okay. These are the even terms. The even terms are left. Okay, and then we take this out. Okay, so then we know that this is this is the error, and then this is what we call second order accurate. Okay, so this is how we arrive at this one. So what you need to do for your homework or tutorial is to do a fourth order accurate second derivative. Okay, in here. This is similar method to calculating the first derivative. Okay, so next we talk about time differencing. It's pretty much the same as what we did. What we did is spatial differencing. So for the temporal differencing is basically the same idea, but we need special considerations. We'll cover that next week, but a simple introduction in here. Okay. If we express this differential equation with a function of g, which is still in terms of your variable. Okay, if your variable is pressure, then your expression should be expressed with pressure, right? So this is a general function of f, and g is also a function of t, of time. Okay, so g. Okay, the examples here. G can be expressed as T. Or this is another example. Okay. So this is what we did for the spatial differencing, and it's analogous to space to temporal differencing or time differencing in here. Okay, we still make use of the current information. N is the number of time step. So current information of your variable, and then this is the like a linkage. This is like a linkage. This link is relating your current information to the future information of your variable. We'll cover more next week. Okay, so backward scheme is just like what we did, the backward differencing in here. So this is the information from the last time step, and then this is the current time step, and we still have like a link function between your current information and the information from the last time step. Okay, so here this is kind of special because we want to use the information of the current time step to calculate what's happening in the future, but we need the information from the future first. So we will cover this next week. We also have a center differencing scheme for the time differencing. This is called a leapfrog scheme. This is a leaping frog, so this is how a frog leap. We're skipping time step in here. Okay, we'll cover more about this next week. So this is more widely used in atmospheric numerical modeling, the center time difference scheme. Okay, so this is just a summary. So what you need to do is that you need to work with Python for the first 3 questions. I think this is first one, and then second, and then third one, and then the fourth one you need to work with by your hand. Okay, you need to do what we just did in this lecture. Okay.